We're going to wrap up our initial study on the fundamental theorem. Remember, the fundamental theorem says that the degree, which is the highest exponent, will always determine or tell us the total amount of roots, the total amount of answers that we'll get for a problem. So we've got the fundamental theorem, and then our last lesson we figured out that we can use some division to help us depress an equation to a simpler equation. There's also graphs that help us sometimes get started. So now what? Well, we're going to look at some special cases. Special cases. The one nice thing about special cases is that we can still use all the ideas that we've learned, but we may need to learn how to interpret or adapt sometimes at the end of the problem, and that's exactly what's going to happen today. So our first special case is going to deal with what's called multiplicity. Multiplicity is a new word. I don't expect you to already know what it means, so let me give you a definition. Make sure that you give yourself enough space to take some notes, but you also probably want to write down that multiplicity is the number of times a root is counted. The number of times a root is counted. Now, what does that mean? Well, I'll share with you that up until now, all the problems that we've done have had multiplicities of 1. That's because every root that we found, every answer that we found, well, it only showed up 1 time. Wait, are you saying that an answer might show up more than once? Yes, that's what we're saying. So let's look at an example. I went ahead and just wrote it on this page. It's a little bit long and big, but it's going to be a polynomial that we're going to look at so we can understand multiplicity. X to the 5th minus 8x to the 4th minus 4x cubed plus 122x squared minus 45x minus 450. Big old polynomial. Now, as you're writing that down, one thing that we can be sure of is that this thing is going to end up with 5 roots. That's the fundamental theorem in action. We're going to get 5 roots. So we better get started. And that's actually kind of the first question. Where or how do we get started? Did somebody say with the graph? That's correct, the graph. If we look at the graph, we might be able to get a starting root like we learned yesterday. Let's switch over to Desmos. I encourage you to use Desmos and type this in and see if we can find some starting roots. All right, so we're typing in x to the 5th minus 8x to the 4th minus 4x cubed plus 122x squared minus 45x minus 450. Now remember, when you guys graph these, sometimes an adjusted window may be necessary. For this particular problem, my x window, is really just kind of going between negative 10 and 10. We've said this a few times that negative 10 to 10 is where you're going to find most of your answers. The y window quite possibly might need to be a little bit bigger. So I'm going to go ahead and sort of pull out to negative 200 to 200 for my y window. It just kind of helps to get a better perspective on the graph. Pretty cool looking graph, eh? Well, the truth is, the only thing that I really need from this graph would be some starting roots. Some starting roots. Do you feel pretty good about the number 3? You should. It's in the graph, it's on the graph. 3 is an x-intercept. How about over here? Do you feel pretty good about negative 2 and negative 3? You should. Okay, because they clearly are x-intercepts. What's going on over here at 5? Maybe I better leave that one go for a while. I already have 3 roots that I can start with. That is, start doing some division and depression. So remember, when you use a graph to help you get started, you still want to show a sketch of that graph. You basically want to show your work. When you draw this sketch, it certainly doesn't have to be perfect. What really it needs to do is just show the x-intercepts that you saw, and it should be showing the end behavior, that is what's happening at the far left and far right of the graph. So I'm pretty sure I saw -3, -2, and +3. I'm going to kind of let this one go over here. I don't really know what I saw there. So it's time to start dividing. And remember, you just need to pick one of the roots to start with. I like the number 3. It's positive. So I'm going to start dividing with the number 3. I hope that you're using your coefficients to create your division problem. I'm not going to overwhelm with a lot of circles and stuff, but 1, -8, -4, 122, -45, and -450. The process begins. Bring down the 1, multiply here to get 3, add these to get -5. The process continues. Multiply to get -15, add to be -19, multiply to be -57, add those to be 65, multiply those to be 195, and add to be 150 so that you can multiply one more time to be positive 450. The beloved remainder of 0. That means that everything is working. That means that 3 was actually a root, and I have myself a depressed polynomial. But it's still pretty big. So now I'm going to move over to my next root. I'm going to move over to, well, I'll tell you what, I'm going to move over to -3, honestly, just so you guys realize that I could pick any one of the roots. Now, I don't want to recopy a bunch of stuff, so I'm just going to write -3 beside my depressed numbers, and, well, I'm going to divide again. So bring down the 1, multiply and get -3 so that you can add to be -8. Multiply to be 24, add them to be 5, multiply to be -15, add them to be 50, and one more time the beloved remainder of 0. Remember, you get a remainder of 0, that means you picked the right root. It also means that you divided correctly. Lastly, I'm going to choose -2. At least at this point, I'm going to choose -2. It's one more root that I'm sure of from my original graph. Bring down the 1, multiply, add, and shoo, I get a remainder of 0. Thank goodness, because I don't know what else I was going to divide by. Now keep in mind that I started with a degree 5, but I divided 3 times. So if I divided 3 times, I'm now down to x squared. That is technically 1x squared, -10x and 25. I'm going to write that more separately, but I'm down to a depressed polynomial of degree 2. Now, kids, when you get to degree 2, you're at a point that you probably can solve with some type of technique of the last month or so of class. In this problem, it looks like I can actually factor. So why not? You know, if you can factor, factor. It factors very nicely to be -5 and -5. That is x minus 5 and x minus 5. And I think I'm supposed to find the roots that go with each one of these, which turns out to be 5 and 5. Wait a minute, 5 twice? Yes, 5 twice. Remember that word multiplicity that we had on the first page? Well, we say that x equals 5 has a multiplicity of 2. That simply means that it gets counted twice. Now, what's the big deal? Well, the big deal, first of all, is that I needed 2 more roots to go with my already 3 roots so that I could have 5 roots. Perfect. I was supposed to get 5. We knew that the degree was going to give us the 5 roots. So that's good. The fundamental theorem is satisfied. But look at x equals 5 on your graph. Look at x equals 5 on the graph. There is a special behavior right here. Now, first of all, x equals 5 actually is a number on this graph. That is that the graph is interacting, it's touching, it's showing the number 5. But there's an interesting behavior here at 5. Do you see how the graph comes down and then goes back up? What are you trying to say? You're trying to say that it touches at 5. And that's because it had a multiplicity of 2. So again, when I have a multiplicity of 2, how do I want to write this? It touches because or with a multiplicity of 2. We get a different behavior. You say, what's different? Well, these x-intercepts, these roots crossed, but this one touched. And when it touches, it kind of just bounces off. And again, that actually was a sign to us that it was going to have a multiplicity of 2. Now, the number 2 is an even number. The truth is, any even multiplicity will always touch. These roots crossed. And when you cross, that's because there is an odd multiplicity. Now remember, multiplicity just means how many times is it counted. And each one of these was only counted once. So the multiplicity was 1. Let's make a conclusion with this. Let's make a multiplicity conclusion. Even multiplicity, the number was counted 2 times. It's going to just touch the x-axis. But odd multiplicity, the number was counted 1 time. It's going to cross the x-axis. Now, could we have higher multiplicities, like a multiplicity of 3, 4, 5? We could. Okay, the most common multiplicities are some of the lower numbers, like a multiplicity of 1 or 2. So, that's our first special case. You ready to look at the imaginary special case? Yeah, now don't let the word imaginary get you all worked up. Basically, it's just going to be the case that we're going to end up with some imaginary numbers. You actually already saw a problem like this. Let's just look at another one so that you can get kind of comfortable. Okay, so here's a polynomial. You can just put it into this last space here. X to the 4th minus 6x cubed plus 25x squared minus 96x plus 144. Now, there's nothing about this polynomial that screams imaginary. Not at least until you dig a little deeper. So you want to do what we have been doing. You want to try to find the roots. So what are you waiting for? We need a graph, right? Yeah, we need a graph. If you have a graph, you might be able to find some roots that you can start with. Back to Desmos. So we're typing in x to the 4th minus x to the minus 6x to the 3rd plus 25x squared minus 96x plus 144. You're expecting some kind of like really cool graph that went up and down and all around. And it turns out that we just kind of got something that looks something like a parabola. Now it's not actually a parabola because it's not x squared, but it does look like we kind of get like a U-shaped graph. What we really are concerned about is the behavior at the x-axis, because that's where we find our roots. What do you see? That's right, you see a graph that's just touching. It's just touching at x equals 3. What does that mean? That's right, we just learned that means that it has an even multiplicity. Most likely a multiplicity of 2, which means that the number 3 is counted twice. So we're going to use the number 3, and then we're going to use the number 3 as our root, as our starting root. So when you use a graph, you always want to draw a little sketch. What really matters about your sketch is the behavior at the x-axis, but you should also be showing the end behaviors correctly. We just got that off of Desmos anyway. So x equals 3. And if you're really on the ball, you would say x equals 3. Yeah, I mean, you can write it twice, because what's going to happen here is we're going to end up dividing twice. We have what's called a repeated root. It has a multiplicity of 2. So I'm going to divide by 3. Let's get this going. I'm going to divide by 3. Keep multiplying and adding. Negative 48 times 3 is negative 144. And again, we get the beloved remainder of 0. Now, I'm going to divide by 3 again because technically 3 is counted twice. Okay, so I'm going to pick up where I left off. I don't want to start back over at the beginning. The cool thing here is that I'm going to depress again. And when I depress this again, I get a smaller solvable polynomial. What am I talking about? We're talking about the 1, 0, and the 16. Now that's a depressed polynomial. Since I divided twice, it's now down to 1x squared plus 0x. We usually don't write the 0x, so I'm going to get rid of that. Plus 16 equals 0. What is going to happen when you solve this depressed polynomial? Well, the quick answer, the short answer is you're going to get an imaginary solution because you're going to take the square root of a negative number. Actually, you're going to get 2 solutions because we get that plus or minus as soon as we take the square root of a negative number. Remember that the negative sign comes out as the letter I, and when you take the square root of 16, when you take the square root of 16, you actually get a smaller number, you get 4. Plus or minus 4i. Kids, that's 2 imaginary solutions. That's positive 4i, and that's negative 4i. And that is great news because now I have 4 total solutions. Those 4 total solutions satisfy that fundamental theorem one more time. Now, what we see here is that the real roots showed up on the graph, but the imaginary roots did not. Don't try to figure out where 4i is on this graph. You're not going to find it. Again, that's because the imaginary roots don't show up on the graph, but they still count. They still count towards my fundamental theorem. Now, to be honest, we've arrived. We've come to the point that you've seen all the types of problems, but of course you're going to have to get good at this. You're going to have to practice it. Today's lesson definitely comes with an exit problem that the students are going to do in class, and I'm not going to do on this video. You're going to want to also do this, even if you're not in the classroom. This is something that you're going to turn in. Okay, now I probably would provide a little bit of guidance in the classroom, the same guidance that's on this screen. You're going to definitely want to get started with a graph using Desmos. Notice that I kind of have like a little suggested window up here, but it would be cool if you can think about making your Desmos graph look good. You should also notice that there's some missing terms. Yeah, there's no x cubed. There's no x squared. So when it comes to the step where you're going to start dividing and depressing, you're going to need to make sure you fill in some zeros into your synthetic division. Okay, but You just got to get started. You got to go get a graph from Desmos. You can just type in the exact equation we got here. Don't worry about the zeros. Just type in those 4 numbers. Get yourself a graph and start dividing. You're looking for 5 answers. Yep, you're looking for 5 answers. All right. After you finish this exit problem, turn it in to me. Maybe next time I see you, and make sure you check out the half sheet homework.